most of you are here. Okay, so today I go on to the next chapter. Okay, all right. Maybe I go on slow. Is there any questions or not? Because sometimes I'm worried also. You all haven't revised or haven't prepared yet, huh? Is it okay if I go to the next chapter? Yes, huh? Okay. Because we still have 4 more chapters, including these, 15, 16, 17, 18. We have until 18 chapters, right? So I think we try to cover as much as possible, all right? Then we can do a lot of revision. We have time, plenty of time, then we can do a lot of revisions. All right, but I try to go slow. The problem is I don't know whether you understand or not. I can't see your faces. All right, okay, so if you feel that you don't understand, please, you have to ask. All right, you have to ask. Okay, you need to understand. If you don't understand, then you very difficult. All right, so try to concentrate. Okay, try to understand, then do the exercises. All right, the practice is important. All right. Okay, so I saw the exercises, they're coming in, very few, not even half have sent me. So it's okay, I mean, I'm not going to push, but I need the exercises. So don't sit on it, don't take your sweet time, So try to do, okay. Every day you do a little bit also, I think you can cover, right? But you must do the exercises, practice, practice is important. You don't practice, then you won't be good, you won't understand the lesson. Okay, so today we are going to chapter 15. Chapter 15 is on direct current, right? Direct current circuit. So direct current means is from a electrical source lah, an electrical source like battery. Okay, like battery, they produce DC voltage. Okay, what we call DC voltage, right? So here, okay, as you can see, DC circuit forms a basic part, okay, basic part of electronics in radio, TV, computers, remote control, okay, sensors, telephones. Okay, so all these they are using DC circuits. Okay, our telephone also using DC circuit. All right, okay, so DC means current that flows in only one direction. Okay, that's easy to understand. Now why we say DC is a direct current, it means it only flows in one direction, current that flows in the direction, right? So the DC components consist of DC voltage supply, consists of resistors, capacitors, diodes, resistors. Okay, capacitors all we have studied, resistors we have studied. All right, so in this lesson we are going to concentrate on DC circuits. All right, okay, they're made up of DC voltage supplies and resistors. Okay, so this is a circuit, alright. So in the circuit you have a lot of components. Okay, so if you are an engineer, so you must know all these components, resistors, diode. Okay, right. Now electric flow is analogous with water flow. In order for us to understand, okay, a circuit, a DC circuit, we can assume it to be like a water flow. All right, easy. Maybe this can be easy for you to understand. Some people, they find it very difficult to understand the concept or the idea how a DC circuit works. Right, so maybe you can compare it to how a water flows. All right, like this. So here they are comparing. The flow of electricity around the circuit compared to the water flow system. All right. So what is the electrical equivalent of the pump? So the pump here is the one who's going to push the water. So what is equivalent of the pump in here? It's obvious lah. It's the dry cell lah. All right, in the dry cell, and the water is Water is the electron or the current, okay, that flows. Okay, current that flows, current is not the electron, the current that flows. Okay, we can say that. All right. So battery is equivalent to the pump, the light bulb is equivalent to the water driven turbine and generator. Okay, this is equivalent to the water, and the charge is equivalent to the water. Okay, the charge, electron is equivalent to the water. Okay, all right, because that's the flow, the flow, right? So this just to understand only, so no need to memorize this, nothing. Just for you to know how the circuit works. So don't need to note down or emphasize on this. Don't want. All right, we just want to know how it works, that's all. Okay, how it works, right? So how the battery works? The battery works just like the pump. The pump drives the water around the system. If there's no pump, the water won't flow. So same like in a DC circuit, there is no battery, there is no current flow or no charge flow, right? Charge is not won't move. Okay, if there is no battery. So you try to understand that, right? So where there is a pump is the one who moves the water, all right, around the system. So same like that, how the dry cells charge move around the circuit, right? So the pump creates the pressure difference. Pump creates the pressure difference because of this push. He able to create the pressure. Okay, so in that case, same as cell. The cell or the battery also creates the potential difference, which enables the flow of charge. Okay, charge flows when there is a potential difference. Same like how the water flows when there is a potential difference. Okay, all right. Okay. Sorry, wait, I didn't start the recording. Oh, okay, started. All right. What about the bulb? All right. So the turbine and the generator converts the kinetic energy of the water to electrical energy. Okay, this is in the pump station. Okay, the flow of the water turns the turbine. When turbine turns, it generates electricity. Okay, so kinetic energy of the water is converted to electrical energy. All right, bulbs also same thing. Bulbs converts the electrical energy to heat and light, because charge brings electrical energy, current. All right, so bulb converts the electrical energy into heat and light. Okay, what about the water? These are the quantities which flow around the circuit or the system. Water and charge are conserved by each system. Conserve means they won't change. Okay, they are the same, will be the same throughout the circuit. Okay, this system, and they are recycled. Okay, they are recycled. All right, they are recycled. All right. Okay, so this is roughly how DC circuit works. Okay, so just concentrate on DC circuit. If you try to understand, then try to compare it to water circuit so that you know how a DC circuit works. All right. Okay, we go on further. Right. Now click on the switch to close. Okay, so we have the flow of the current. This is the current flow. The arrow shows the current flow. It goes to a resistor. When it goes to a resistor, heat will be dissipated. Okay, so cells are the sources of the electrical energy, which causes the charge to move in electric circuits. They have traditionally been called sources of electromotive force. That's why cell, we call them as a electromotive force. Although there is a word force here, remember here also they repeating. They are the word force here, but they are not actually a force, but they are a source of energy. It is a source of energy. So don't say this is a force. The cell is a force, is a source of energy. Okay, but it is known as electromotive force. All right, because it causes the charge to move. No cell, the charge won't move. All right, so that is why it's better to use the term EMF. So that's why we don't write in a longer sentence or longer sentence, because sometimes students confuse with the word source, force here. All right, is not actually a force. Is a source of energy. Is a source of energy. So we write in short form. So now from onwards we use the short form EMF. In exam you can use EMF, no problem. It's not wrong, although it's a short form. Okay, you can use. It's a universal term, abbreviation that we use. So it's not a problem. So you can use EMF. Understood? Right? Okay. So what is the definition for EMF? EMF of a source is the potential difference across its terminals when no current is drawn from the source. Okay, so when there is no current flow yet, right, and you take a potential difference across the cell, that is the EMF of the cell. All right, so a cell is said to have an EMF of 1 volt when it supplies 1 joule of energy to 1 coulomb of charge passing through it. Okay, so what is the definition of EMF? So let's say EMF of 1 volt. EMF of 1 volt means what? It means that he is supplying 1 joule of energy to 1 coulomb of charges as they pass through or they leave the cell. As they leave the cell, right? So 1 joule, 1 volt equals to 1 joule per coulomb, right? Per coulomb, right? So this is a simple calculation. In a circuit of 0.25 coulomb of charge, which gains 3.0 joule of energy from the cell. What is the EMF of the cell, right? So EMF of the cell is energy provided by the cell divided by charge. All right, this is another definition. Maybe just now we didn't explain. All right, here we can they are explained here. Right, EMF is equivalent to energy provided by the cell divided by charge. Okay, charge that comes out of the cell. Okay, all right. So this is the energy provided by the cell, 3 joule, and the charge in the circuit, which is a charge from the cell, which is equivalent to 0.25. So the EMF of the cell is 12 volt. Okay, right? So if you notice just now, EMF, the unit is volt, volt, right? So EMF is different than here, potential difference. Although they share the same unit, volt, right? So what is the definition for potential difference? So potential difference between 2 points is the energy required to move a unit positive charge from one point to the other point. So it's between 2 points. Must have 2 points. Alright, so between the 2 points, then only we can find the potential difference. So what is the potential difference between these 2 points? Is given by energy required to move a unit of energy required to move a unit positive charge, right, from this point to this point. So how much energy is needed? That's a definition for potential difference. Okay, right? So when 1 coulomb of charge passes through this bulb, it dissipates 6 joule of energy. 6 joule of energy. It means 1 coulomb of charge passing through the bulb here okay, it gives out heat of 6 joule of energy. Now using the definition to work out the potential difference across the bulb, so what is the potential difference across the bulb? So the potential difference across the bulb is 6 joule per coulomb. Remember, unit positive charge, energy is required to move unit positive charge, right, from one point to another. So let's say 1 coulomb of charge is moving. As a result, 6 joule of energy is being dissipated, right? So how much is the potential difference between these 2 points, right? So potential difference is given by 6 joule per coulomb. 6 joule per coulomb, or in other words 6 volt. Okay, 6 volt, right? Any questions here? Okay, so far okay? Can you follow? Can? Yeah, okay. Now, so when a current flows through a resistor, heat is dissipated, right? When heat is dissipated, heat means energy lah. So energy lost, right? So there will be an energy loss. Okay, so there is also a power lost, right? So when energy lost by 1 coulomb of charge as it passes through the resistor is V, alright, therefore the energy E lost by Q coulombs of charge is given by this equation, E equals to QV. Energy lost by Q coulomb of charge is equivalent to Q times V, right? This is based on definition of potential difference just now. Alright, definition of potential differences now. Okay, V equals to E over Q. So E equals to QV. So power, what is power? Power is, if you remember, power is the rate of change of energy. Right, rate of change of energy. Alright, is supposed to be dE over dt. Alright, dE over dt. Alright, okay, so E here we replace with QV. This is wrong, this is supposed to be oh, this is wrong, no Q here, E is supposed to be here, dE over dt. Okay, this is wrong, hello, okay, wrong, this one is supposed to be dE over dt, no Q here, E must come here. Alright, dE over dt, that is the rate of change of energy, dE over dt. Now E replaced with QV, then you get this. Are you following me? Alright, hello, okay, alright, okay, so this is wrong, this is supposed to be dE over dt. Alright, so E we replace with this, then you get this, right? Okay, so what here will be potential difference across the resistor will be constant, so we bring it out. The one is changing is dQ over dt. dQ over dt is, we know, is equivalent to rate of change of charge, rate of change of charge, or rate of change of charge is equivalent to I, current. Okay, so in other words, power, right, power dissipated, alright, power lost here in this case is equivalent to IV. P equals to IV. Okay, okay, that was power dissipated. Now power from a source, just now was a resistor. Resistor is not a source. Now we are using a source, a battery. So power supplied by a cell. So we say power supplied. Don't use, you must use the correct term. Don't use wrong term when you are describing power, right? Power that comes comes from a cell is power supply. Okay, power supply. All right. So power that you get from a resistor, like example just now, from a resistor. Resistor, you cannot say power resistor does not supply power, so you don't use power supplied by the resistor. This is from a resistor we have energy lost. It means the power lost, right? So it's a power dissipated or power lost, we can say that. Okay, so you must use the correct term. All right, don't use any term. All right, so here we're talking about cell. Cell supplies energy. Okay, so when there is an energy, there is a power being supplied too. So power supplied by a cell. All right. Okay, so energy here gained by 1 coulomb of charge passing through the cell is equivalent to epsilon. Okay, epsilon. Epsilon is the EMF of the cell. Therefore, energy E gained by Q coulomb of charge, right, is given by E. E is energy from the cell is equivalent to Q times V. If you remember, Q times V. But our V here is this EMF, right? So that's why we use, instead of V, we use epsilon. Okay, epsilon represents EMF of the cell. Okay, so power supplied by the cell is equivalent to the power gained by the charges. So as the charges move, right, so they are moving with a certain power. What is their power? The power that is supplied by the cell. So that's why we say it like this. Power supplied by the cell is equivalent to the power gained by the charges, right? So we replace, okay, again, all right, all right. So again, following the earlier equation, power equals to dE over dt. D energy, d energy over dt. Right? So the energy here, this E, dE over dt. So E here we replace with the Q epsilon. That's where we get this. Alright? Okay, that's where we get this. Alright? So epsilon here is constant, so we can bring it up. The one is changing is dQ over dt. So power P here is equivalent to I epsilon. So this is the power supplied by the cell. I epsilon. You see the difference here? Alright. So this is power supplied by the cell. Okay, power from a source. Now any questions here? Anything you want to ask me here? Alright. I don't want to go fast. I just want you all to understand. So don't get confused with di and d epsilon. Sorry, I epsilon and IV. IV. Alright, I epsilon and IV. Like here, this is IV. P equals to IV. So when you talk about power from other components, so we use V. Alright, but when you talk about power across power supplied by a cell, so we never use, don't use V, you must use epsilon. Alright, power equals to I epsilon, because epsilon here represents EMF. Right, EMF. Okay, any questions here? No, Okay, I assume you understand. I assume you are listening. Alright. Can only hear one or two voices. Others are very quiet. Alright, here is one example. Okay. Calculate the power dissipated by a 20 ohm resistor in this circuit. Then deduce the power dissipated by 10 ohm resistor. Okay, 10 ohm resistor. Okay. Can you hear me? Can because I thought, oh my, the other one have left. Okay, that doesn't matter. I'm still here. The main one is still here. All right. Okay. Can you see the video? The video is still there, isn't it? All right. Okay. So okay, I go carry on. All right. So the power dissipated by 20 ohm resistor. 20 ohm resistor is. All right. Okay. So we have to calculate. So power dissipated. All right. We already defined just now. Power dissipated is equals to IV. So I here equals to V over R. Right. So V across here. All right. So V across here. This is what? Power dissipated by 20 ohm resistor. Right, so they are using current that flows through here is equivalent to the current that flows through here. Current is, this is in series, so the current that flows through is the same. So we can use these two info to find the current that flows through. So they are using that to find the current that flows through. Right, so then we use the equation that, okay, to find the power dissipated in 20 ohm. All right, power dissipated in 20 ohm is equivalent to I times V. Our I here is 0.5. Our V here, okay, is 10 volt. So it's 10 volt. So power dissipated by the 20 ohm resistor is 5 volt. So we use the same method to find the power dissipated by the 10 ohm resistor. Right, again use the same formula. IV, I is the same, 0.5. V here is across the 10 ohm resistor is equivalent to 5 volt. So it's 5 times 0.5 is 2.5. Okay, right. So very important, you must know the difference between EMF and potential difference. Alright, so EMF is defined as the energy supplied to each coulomb of charge by the source to drive the charge around the complete circuit. Okay, so potential difference between 2 points in the circuit is the energy required by 1 coulomb of charge to move from between 2 points. Between 2 points. So both of them have the same unit, volt or joule per coulomb. Power dissipated by a resistor is V times I. Power output or supplied by a cell is equivalent to EMF times current. Alright, EMF times current. This is V times I. This is epsilon times I. Okay, but both are the same. But here is power dissipated. Here power supplied or output power. Okay. Okay. Can you follow so far? Right. Okay. This is just the basic understanding of your this one, EMF. EMF. Right. All right. So in this circuit, we have placed a high resistor voltmeter across the terminals of a dry cell. Click the switch to complete. Okay, let's complete the circuit. All right. So when we click, okay, immediately we click, we get a reading. This is the reading of the EMF of the cell. So that's what they ask. What is the voltage across the terminals of the cell? The voltage is 1.5. Right. So 1.5 volt. So this is the EMF of the cell. Right. Now, since the resistance of the voltmeter is very high, okay, resistor of the voltmeter, actually there is a built-in resistor inside the voltmeter. This is very high, right? So when it's very high, we can assume that this is the voltage across the cell because there is no current be flowing here inside here. Okay, right? Just a little bit, but not through the sun because of the resistance which is very high. Right? So this reading here is the close approximation of the EMF of the cell. Okay, so this shows the reading of the cell. All right, so that will be the EMF, right? Okay, now we have been added a resistor in the circuit. When we have added resistor in the circuit, the current have to overcome the resistor, then only can flows through the voltmeter, then you have the reading. So when we take the reading with the resistor there, we get a reading of 1.35. 1.35, right? So if we are going to draw these in the form of a circuit, this is the how we are going to draw, all right? So there is a cell, this is the cell, then there we have the resistor which is in parallel, okay? This is in parallel, right? So that's why this resistor in parallel, and the voltmeter, right? So the reading is 1.35, right? Now voltage across the cell is 1.35, which is less than the EMF is 1.5. Now the difference of 0.15, the difference of 0.15 is called the lost voltage, right? Lost voltage, because cell we actually we measured 1.5, right? Now it is giving 1.35, right? Okay, so there are lost of what is it, voltage, which is due, okay, where is the loss? Okay, this loss is due to the voltage drop across the internal resistance of the cell. So inside here itself we say there is an internal resistance, right, of the cell. So every cell will have an internal resistance, all right? So the internal resistance of the cell is equivalent to which makes the voltage that really actually that comes out is around 1.35. So there is a loss of 0.15 because you have to overcome the internal resistance, right? He have to overcome the internal resistance, then only the voltage can be supplied outside. Okay, so inside the cell itself, he has internal resistance. Okay, so from now onwards we're going to use the internal resistance of a cell, right? Okay, so here we can see how effective it is, the internal resistance. Now what is the combined voltage of 8 dry cells? One dry cells we know is around 1.5, isn't it? So 8 dry cells combined, right? When we combine 1.5 times 8, 1.5 times 8 is how much? 12 volt, right? Okay, it's 12 volt, all right? So when we join the terminals, okay, nothing happens, all right? So but total is 12 volt, all right? Okay, now we change that 8 cells, okay, we replace with 12 volt cell, 12 volt acid battery, acid battery, right? Now we join those, you'll see a sparkle, yeah. My screen missing, oh, okay, I went out already, wait, okay, now okay, all right, okay. So just now you saw the 6 cells, 8 cells, right? 8 cells, right? So our total is 12 volt. We join the terminals, nothing happens, all right? Now these same 8 cells we replace with a 12 volt cell, okay? And we join together, you'll see sparkles, right? How come? Right? How come here is also 12 volt? Earlier also 12 volt, right? But here we won't see any sparkles. But here when we are using a 12 volt lead battery, 12 volt lead battery, all right, we'll see sparkles, right? Okay, why do you think is that? What do you think is that? Why do you think there is a sparkle here? Any idea? Okay, right, that's because of the internal resistance lah, internal resistance, right? So the voltage of two power sources are both 12 volt, right? So why does the dry cell here produces a sparkle? Because the internal resistance of the lead acid battery is very small. Okay, so they produce a large current, okay, a few hundreds ampere, okay, which produces a sparkles when you are short circuit. When you short circuit it, it produces sparkle. Whereas here we use cell, each cell have internal resistance of R, okay. So imagine a total is how much, so the internal resistance is very big, so the current that actually flows is very small, alright, is small, so it's not enough to give you, although short circuit is not enough to create the sparkle, okay, create the sparkle. Here only one cell, alright, but so that is has a very small internal resistance which produces a larger current. Okay, okay, right. So let's now onwards, okay, so we're going to consider the internal resistance. So internal resistance, we always use a small r to represent internal resistance. Okay, the unit still ohm. Small r means is internal resistance. So who has the internal resistance? Usually is the cell. So any cell is given, any dry cell is given, it must have internal resistance. They question didn't tell you also, you must know, you must consider, right? So potential difference across the cell, right? Potential difference across the cell, right? Now there are two things here. Here you must understand here, right? One is this is the potential, this is the what? This is the EMF. It means the voltage supply. This is supply, right? But this voltage supply, you have to overcome the internal resistance, right? So there will be a potential difference across here, which is given by IR. So IR is equivalent to the potential that he have to overcome, right? This is what is supplied. So what is actually coming out? What is the potential, the voltage that is coming out from the cell? Is epsilon minus IR. Are you following me? Very important concept, you must understand. So what is actually coming out of the circuit? Okay, potential that is supplied to the resistor here. The potential that comes out from the battery here is epsilon. Epsilon is the actual voltage or actual EMF, electromotive force of the cell, right? Voltage of the cell, but he have to overcome his internal resistance. How much? He have to overcome this voltage, IR. So this much of voltage will be lost, will be gone. So what is left? So what is left is epsilon minus IR. That only comes out or goes into the circuit, right? So what is the expression of the terminal potential difference V in terms of EMF and the lost voltage? This is the lost voltage, right? So what is coming out, which is equivalent to the V lah, V, the voltage or the potential difference, the potential difference between the terminals. That's what they said. That's what is coming out is the potential difference between the terminals, right? So V, all right, V, this is the big V, V equals to epsilon minus IR. I told you, right? This is what actually coming out. This is the what creates the potential difference between the cell, right? Okay, okay. This one you have to understand, try to understand. You understand? Then easier. So the same voltage is what makes the current flow, the potential difference. This is what they mean, terminal potential difference. Okay, what voltage that is comes out. All right. So usually in book they use V equals to epsilon minus IR. Okay. Right. In this interactive model can be used to explore the effects of internal resistance in a circuit. What happens to the voltage across the load? Okay, this is the load. Load is always refers to the resistance. When R is very large compared to the small r. Small r is the internal resistance. So small r, always look at internal resistance. Internal resistance is always inside a power supply or cell, right? So when your this r is very much bigger than this, right? They ask what happens to the voltage across the load, across here. Okay, so see what happens when I increase the resistance. This resistance now is 0, so the voltage is also 0, right? Voltage across the resistor is also 0, right? So I increase, see what happens. Okay, okay, so 1.5, right? Resistor, the load resistor of the load is 1.5, which is very much bigger than the internal resistance 0.5. So we have the voltage of 1.1 volt. Okay, so what happens when the voltage across the load is almost equal to the EMF? You see, voltage across the load, which is 1.5, okay, all right, voltage across the load is almost equal to the EMF. When your R here, when the R here is big, okay, compared to this, all right, so the voltage across the resistor is increases until it becomes almost same as the EMF, almost same as the EMF, right? Okay, almost same as the EMF, right? So voltage across the load is almost equal to the EMS 1.5. Actually you minus there, you get this lah. Okay, all right, yeah. Bigger than uh-huh uh, if it's too big, then there won't be a flow, right? You're telling this lah, if it's bigger than so it's bigger, the maximum he can go is 1.5, right? The maximum he can go is 1.5. In this case, the maximum that he can go is 1.1, because you have the internal resistance also, right? So you increase some more, this one you load, you load some more, that's the maximum. You already reached your maximum already, right? So he will, the maximum is 1.5 lah, that's all. That's why he said when you increase the load, it will become almost equal to the 1.5. All right, why they use almost? Because he still have to overcome the internal resistance. All right, so you won't exactly get 1.5, but you can get nearest to it lah, very near to it. Okay, but it won't be more than that, definitely won't be more. Okay, all right, okay, all right. So this is another circuit. So in this circuit, the internal resistance is fixed at 0.5, right? So alter the resistor of the load. Okay, we're going to alter the resistor of this load. observe what happens to the power dissipated. Power dissipated, okay, all right. Sorry, power dissipated from the load, okay, all right, as we increase the R, okay. So power across the load is dissipated across the load is given by this equation, I to power 2 R is IV, but we can use this equation also, I to power 2 R, because we are varying the R, we are changing the R, okay. So when R equals to 0.5, notice here R equals to 0.5, power dissipated is maximum, okay. Power dissipated is maximum when R equals to 0.5. Now 0.5 is also our internal resistance, okay. So see what happens if I increase further. Power dissipated become less, no more maximum, although the resistance is more than 0.5. okay, I increase some more, okay, right. So when is R equals to 1.5, okay, is almost it goes, power dissipated is almost goes to 0, right, almost 0, right, very less. Why is it like that? So what do you observe? Power is maximum when R equals to small r. Please note this down, okay, because sometimes they ask to calculate the maximum power. So maximum power, you get the maximum power when your outside resistance, okay, which is your R, big R, is equivalent to the internal resistance, small r, okay. So please note it down somewhere. The power, maximum power dissipated by the R outside, okay, by the R outside here is happens when R equals to the internal resistance of the cell or the power supply, okay. All right, so this is a PR graph. All right, so we do the calculations for power that involves what is that? Involves the internal resistance. Now remember, right? This is the earlier equation, right? The voltage or the potential, the terminal potential difference from the cell, all right? Okay, is actually this. This is only the cell without the resistance, all right? The actual value of potential voltage supplied, okay, is V equals to epsilon minus IR, okay, this is the lost voltage, so V, all right, is the voltage supplied. This voltage supplied is also goes to the circuit, all right, the R, okay, here, all right. So what is goes here? The V is goes here. So V across here is I times R, okay. V across here is I times R. That's why the V here is I times R, big R, the resistor, outside resistor. Okay, so I, okay, the current that flows in the circuit is equivalent to epsilon O over R plus R. Okay, this one lah, this equation, right? We change the topic to I. So you get epsilon over R plus R. Okay, now to calculate the power dissipated by load is equivalent to I power 2 R. Okay, this is the equation for power dissipated by the load. So replace our I here with this, so we'll get this equation. Okay, epsilon over R plus R bracket to power 2 times R. Okay, so based on this, alright, based on this, alright, we increase the R, okay, we increase the R, we will get this. So R maximum, you see, the power maximum, when your big R is equivalent to the small r, right? Small r, remember, is the internal resistance of the cell. Then after that, it comes down. Okay, the power comes down, right? As you increase your R, you won't get a maximum again. So maximum is here. So this is where you get the maximum power dissipated, okay, lost, okay, hilang, okay, maximum power dissipated. So these, okay, we can get this graph based on this equation. All right. So the power is maximum when the resistor of the load is equal to the internal resistor. Resistor of the load equals to the internal resistor. Okay, I told you just now so many times. Please note this down. Okay, so you want to calculate the maximum power of the circuit when your resistor of the load is equivalent to the internal resistor. Okay. Now, is the internal resistor useful to a battery? No. Okay, because internal resistor decreases the useful power of a battery. All right. So nowadays, that's why the battery manufacturers, they aim to minimize. Okay, minimize. All right, the internal resistance, so that the battery becomes more effective and can last longer. All right, can last longer. Right. This is an example of a question. Okay. Current in the circuit. So how to calculate the current in the circuit? Okay. Right. So we can directly use the equation just now. Remember, if we have this kind of circuit, this circuit is equivalent to, because consider the small r and the big R is equivalent to this. So remember this equation. If you want to go to find the current in the circuit, I equals to epsilon over R plus R. Epsilon is the EMF. EMF is 12 volt, right? Big R is the load outside. If you have two loads, let's say we have two resistors, then you have to combine. You have to combine to get one resistor, total effective resistor, right? And plus the small r. Small r is the internal resistor of the cell. All right. So you put all in, you'll get the current that flows in the circuit. Okay. So sometimes there are questions. They will give you three resistors in the circuit. It must be in series, or in parallel. Doesn't matter, right? But you have to combine all to get one effective resistance. Then you can put inside here. Okay. They can give you like that, right? So what is the terminal voltage of the cell VAB? When you talk about terminal voltage, it means what is actually voltage that actually supplied by the cell. So you have to minus, right? It means 12. Remember or not? Epsilon minus IR. Okay, epsilon minus IR. Okay, epsilon minus IR. You can do that, or you can use this. Right, here they straight away use this. The terminal voltage of the cell is equivalent because they are in parallel. So equivalent to the potential difference across here, must be equivalent. All right, potential across here is equivalent to IR. Okay, so I, we already calculated here, R. Okay, you get. So the power dissipated by the resistor, so P equals to IV, or you can use P equals to I to power 2 R, depends lah. Alright, so here they're using I to power 2 R because R is already given there, right? So I also we know, okay? So we might as use info that we know, so we get this. Then power dissipated through the cell. Now power dissipated through the cell is, right? It's because of this only, right? Is because of this, power dissipated is because of this resistance, right? So it's small r, not big R. Please note this. This is small r. That's why you see the value here 0.5. Is this value? It's a small r. Power dissipated in the cell. So power dissipated in the cell is because of this small resistance. That's why battery, sometimes you keep longer, right? There are loss of energy or loss of power. They are loss of power because of the internal resistance, right? Internal resistance. This is the value. Same lah. The equation is the same. Only thing, this is not small big R. This is small r. this R. Okay, and the values is 0.5, so you get this. Alright, simple calculations. Okay, anything you don't understand that? Alright, okay, so I assume you can follow. So we looked at about internal resistance of a cell, right? Okay, is caused by resistance experienced by the charge as it moves through. See, this is because of a chemical reactions that happens inside the cell. If you ask why there is an internal resistance, that because of the chemical reactions that happens in the cell, right? So it somehow creates a resistance. All right. So internal resistance causes a decrease in useful potential difference across the terminals of the cell. So across the terminal of the cell, the actual potential voltage that being supplied is equivalent to the EMF of the cell minus the lost voltage IR. So V equals to epsilon minus IR. Right? So the power dissipated by a load is maximum when the resistor of the load, the big R, is equivalent to the internal resistance, small r. Remember, the big R equivalent to the small r. That's when you get the maximum power dissipated by the load. Internal resistance decreases the usefulness of the power, useful power of a cell. Right? Actually, it's not a good thing. It's a bad thing. Okay. But nowadays, manufacturers, they are finding ways to minimize the value of the internal resistance. That's why nowadays we get a cell or battery that can last longer. Okay, because they have minimized the internal resistance. So they make the battery effective and longer lasting. Okay. Right. All right. Any questions? I know so much to go. Take your time, go through. Alright, so then you practice yourself. Alright. Any questions? Any questions? So come back to your book. If you are referring to your book, I think 15.1 we have covered. Alright. Okay, so you go through again. Any part that you don't is not similar to what I give you, you just ask me. Actually, it's all there. It's all similar. 15.2 I haven't come yet. Okay, that one maybe we'll do on Thursday. Yeah, Kirchhoff law. So 15.2 you just hold on for a while. Alright, so you can do 15.1. Exercise 15.1 you can do. Okay. Okay. Now 15.2, okay, I leave out for a while. But then if you look at the number 6 there, number 6 is the definition on page 147. Hopefully you have book with you. Do you have your book with you? Should you're at home. You should have your book with you. Right? I think can is not Kirchhoff law 15.2 only. Okay, actually it can. Alright, number 1, number 2, number 3, I think you can follow because they only talked about the potential difference. Potential difference. We already seen that potential difference 2 point. Right. So what I want to show you is the look at page 148. That's interesting. Okay. Many times they have a question like this. 148 number 10 there. Finding the potential change in a circuit. Alright. So try to understand that concept. It's very important. You must understand. Alright. Especially the table there, the figure based on the figure 15.8. From A to B is positive 20 volt. Positive 20 volt because you have a direct. But from B to A, if they ask to find the potential difference between B to A, from B to A, it's the opposite direction. It's the opposite direction of the flow of a current. right? So that's why it's a negative 20 volt. But it must be the same because the points are the same. The potential difference between these 2 points, the value, the magnitude will be the same, right? But why is it positive? Why is it negative? One positive because it's if A to B is a positive, it's in the same direction of the flow of current. But B to A means you are looking at the opposite direction of the current, flow of current. So that's why it's a negative. But the value, the magnitude is the same. Are you following me? Okay, right. So same goes for B to C. Okay, B to C, of course, they use the calculation lah. All right, to find the potential difference. Right, the current that flows is 20 milliampere. Okay, there is a value given there in the circuit. You look carefully after the C. That after the C is 20 milliampere. That's the current. So current times with your resistor will give you the voltage, right? So is 6 volt. All right, it should be 6 volt. B to C. All right. Why is he put negative? It's not negative. It's positive. Why is it negative? Negative 6 volt. Then B to C. That I think is wrong lah. It should be B to C is 6 volt. C to B is negative 6 volt. B to C because all is in the flow of the current. So that you have to make a correction there. All right. 0.02 times 600 volt is B to C. The change is 6 volt. Right. C to B is negative 6 volt. Right. A to C, you see, A to C is overall. Overall. So overall, we can take very simple. At A is 20. At C, right? At C is how much? It's 6, right? At C is 6, right? So it's minus. So 20 minus 6, right? 20 minus 6, right? All right. C to A is the same thing, just change the symbol. Okay, 6, then minus 20. All right, it's opposite direction, negative 14. So there are many examples given. Okay, many examples given. Okay, this is all direct examples. I think it's interesting you do that. Okay, you understand the potential difference at different points. Okay, so I think 15.2 we can do, no problem. Okay, then we come to Kirchhoff law. Kirchhoff law later. Interesting, okay, because it involves a lot of calculation. Kirchhoff law. All right. So I like Kirchhoff law. So do exercise 15.1 and 15.2. Okay. Any questions? Hello? No questions, huh? Okay, hopefully it's done. I try to prepare the videos, okay, and sometimes the video gets longer time to prepare. But this time I'm recording on my own, so I think shouldn't be a problem. I try to put up so you can go do the revisions. I also put up the videos of the previous lesson starting from chapter 12. I'm recording now. Then I think I can put up by today. So those who have missed out, those who don't understand, please go back, refer to the videos, okay, try to go through, okay, any of the facts that you don't understand, right? Not everyone can get a chance to refer to the videos, okay, so this time PDPR, so okay, we can refer to the videos. Alright, so do your revisions and please send me the exercises as soon as possible. You already passed your timing already. Yesterday tutorial is supposed to do the past year for me. I think only 6 of you sent me. Others all missing. Okay, probably doing other exercises. Alright. So today we got another 2 more exercises. So every day do. Okay, you are sitting at home only. So do little by little. I know it's very difficult. Sometimes you do on your own, alone. It's very challenging. Okay, but you have to. All right. So don't give up. All right. Have to. All right. So if it's nothing, we stop here. I'll see you on Thursday, 9:30. Okay. All right. All right. Thank you. Thank you. Thank you. Thank you.